Hello everyone. Today I would like to briefly talk on the progress on ET partitioning project. Evapotranspiration is the sum of evaporation and transpiration. Evaporation is considered as a non-productive water use and transpiration as a productive water use. ET is a key component of the hydrological cycle. It can account for up to 95% of the water budget in dry agriculture. In the last 2 decades, eddy coverage method has been widely used to measure ET at the landscape or field level. However, this eddy coverage method cannot provide separate measurements of E and T, even though it provides direct or continuous measurement of ET. It is difficult to determine individual components of E and T at the landscape level through measurement. There are several implications of ET partitioning for the water budget and actual crop water demand, mechanistic understanding of biological and climatic controls of E and T. Partition E and T are required as input, calibration, and validation data for numerous hydrological and land surface models. ET partitioning is crucial to minimize the non-productive loss of water and to improve water management practices and productivity of agro-ecosystems. However, the partitioning of ET into E and T is still theoretically and technically challenging. We use FVS-based ET partitioning method. The FVS means the flux variance similarity method, which was proposed nearly a decade ago to partition E and T using high-frequency eddy covariance data. This method has a significant advantages such as logistical ease of use and spatial temporal representativeness over other partitioning methods such as microlithimeter, isotopic composition, and shaft flow. This method requires only the existing high-frequency eddy covariance data. Thus, this method has a unique potential for retroactive partitioning of fluxes using existing eddy covariance data records. How does this FVS partition eddy fluxes? The FVS method quantifies the dynamics of E and T by examining the correlation between CO2 and water vapor fluxes. Maximum anti-correlation between CO2 and H2O fluxes generally occurs at around noontime, when vegetation is the largest sink of carbon and at the same time is the largest source of water vapor through the same stomata. And decorrelation of these two, CO2 and H2O fluxes, or dominance of non-photosynthetic fluxes, such as respiration and ecosystem, results in a positive correlation between carbon and water vapor fluxes during evening, night, and early morning, as you see in this image figure here. So during noontime, you see the maximum anti-correlation, which is almost close to -1. And then any deviations of this QC correlation, the correlation between carbon and water vapor fluxes, from this expected ±1 are used to determine the relative amounts of instrumental and non-instrumental fluxes. In other words, for ET partitioning, relative amounts of E and T. Here I would like to briefly talk about a few published articles. The first one was to partition ET using this FVS method over rainfall alfalfa field using high-frequency eddy covariance data. Here we try to look at how that rainfall and hay harvest affected ET partitioning. So the comparison of ET, if you see in this top figure, when we compared ET between pre-harvest and post-harvest days, then you barely see the difference because there was heavy rain on April 29. Because of that, the soil was wet and there was lots of contribution from E. So even though pre-harvest or post-harvest, the ET values were similar. And harvesting of hay was clearly reflected by the carbon uptake. If you look at the bottom figure, the gain of carbon by the system, then it was substantially different during pre-harvest and post-harvest. Effect of hay harvest on E and T. The previous result was further supported by the partitioning of E and T on those days. If you see here on the top figure here, the magnitude of T on May 1, which was pre-harvest, was almost double than on May 4, post-harvest, though ET values were similar in the previous slide. The FVS method accurately predicted dynamics of tea for pre-harvest and post-harvest days. When we calculated monthly T and ET ratios for the whole season, for 2 seasons of alfalfa growing season, T accounted for at least 70% of the ET in each month of the growing season of alfalfa. And evaporation was at least 15% even during dry and hot periods during peak growth. These results indicate that E is not negligible any time as assumed previously by several studies and modeling exercises. The growing season average T and ET was approximately 0.082 in 2016 and 0.77 in 2017, which was relatively wetter year. So the second work was evaluation of different water use efficiency algorithms for flux variance similarity based ET partitioning method, and we evaluated in multiple C3 and C4 grain crops. Several models can be used to estimate leaf level water use efficiency, which is the only input for the FVS partitioning. Leaf level water use efficiency is computed from ambient and intracellular CO2 concentration and ambient and intracellular H2O concentrations. We evaluated 4 parametrization of intracellular CO2 concentrations. Those were constant ppm, constant ratio, and linear and square root functions of vapor pressure deficit. And then there was another one, the 5th one was optimized water use efficiency approach, which is directly calculated using eddy covariance data, and there is no adjustable parameter like in other 4 previous parameterizations. And we used 1 month data during peak growth. And then those C4 crops were maize and grain sorghum, both irrigated, and C3 crops were canola, soybean, and wheat, all rain-fed. Here what we see that we saw the varied performance of 5 different water use efficiency algorithms on number of partitioned outputs. Discrepancies in the number of successful partition outputs were mainly caused by incompatible water use efficiency estimates due to their different assumptions and requirements. As you see in the table, there's a breakdown of everything there for these 5 algorithms. Optimum model resulted in the fewest partitioning solutions in all crops. Constant ppm and constant ratio models consistently resulted in large number of successful half-hourly partition fluxes for all crops except soybean. In soybean, linear and square root models produced more partitioning results. And we also observed large discrepancies in water use efficiency estimates for these 5 different algorithms for different crops. And we also observed large discrepancies in the range of T and ET ratios for these 5 algorithms. Range of T and ET ratios found with 5 algorithms was 6 to 8% difference in soybean and maize, 12 to 13% difference in maize, wheat, and canola, and up to 22% difference in T and ET ratios for grain sorghum. The crops producing larger variation in computed T and ET ratios tended to have higher discrepancies in estimated water use efficiency for these 5 water use efficiency algorithms. When we looked at temporal differences in T and ET ratios during wet and dry periods, linear and square root models failed to produce reduced T and ET ratios during wet periods in all crops except soybean. The constant ppm and constant ratio models showed better potential to partition ET in all crops except soybean. In soybean, linear and square root models produced better. Probably the reason is modern soybean cultivars exhibit greater isohydric behavior. That means they maintain a constant midday leaf water potential during wet and dry conditions. That could be the reason that soybean behaved differently than other crops. And also, the same water use efficiency algorithm performed differently in different crops. Most likely different canopy structures and canopy coverage, growing season in winter, spring, or summer, environmental conditions, because in summer we have high temperature and BPD, but spring and winter, those crops may not experience those high temperature and BPD beyond their threshold limits. So this type of study to evaluate these different factors requires further investigation. T and ET ratios varied substantially for different water use efficiency algorithms during wet periods, but they were comparable during dry periods. Substantially larger T and ET ratios and fewer successful partitioning solutions for the linear and optimum models indicated uncertainty for their applicability in C4 crops. Stomata may not behave optimally in C4 species during water stress conditions or even at higher temperature and VPD because they can maintain high photosynthesis even under decreased stomatal conductance because of their CO2 enriched mechanisms. Our results illustrate that the choice of water use efficiency algorithm can cause large differences in partition fluxes. The optimized water use efficiency approach, which has no adjustable parameter and it is computed directly from eddy covariance data, can have a potential as a benchmark for comparing other water use efficiency algorithms in C3 crops. And there is a third work which is published as ecosystem level water use efficiency and ET partitioning in conventional till and no-till rainfall canola. Here, I'm showing here the patterns of EVI and fluxes. Large differences in EVI and fluxes were observed between CT, that means conventional till and no-till fields, from mid-February to mid-April due to poor post-winter recovery in no-till. Large differences, February-April period, large differences in transpiration than ET illustrated more evaporative loss of water in no-till field due to sparse canopy during the wet spring period. Seasonality and proportion of T and ET ratios. Seasonal T and ET ratios were identical, which was around 0.70. So the 70% of ET was transpiration in both fields, even though one field has a sparse canopy and one field had a dense canopy after that winter recovery. This result was somewhat unexpected considering differences in vegetation phenology between two fields. However, this can be attributed to the cancel out effect of evaporation from intercepted rainfall by vegetation and swell with regard to discrepancies in vegetation cover. Because if you have a dense canopy, then you may have more E from intercepted rainfall by the vegetation. And you can have a high E after rainfall from wet soil if you have a sparse canopy. So it looks like there is a cancel out effect. And that should be the reason for seeing identical T and ET ratios, even though there was a contrasting vegetation structure like dense and sparse canopy. And when water use efficiency was calculated based on ET and T, water use efficiency was overestimated based on ET during the periods of higher E. Partitioning of ET could minimize the bias of cross-site comparison of water use efficiency, highlighting the added benefit of T estimate. If we can have a T cross-site comparison, and if we calculate water use efficiency based on T, then we may directly compare results better than this ET and lots of other confounding factors on ET. Partitioning of ET or independent measurements of T or E can provide further insights on the coupling between carbon gain and T, as E is not directly related to the canopy function. Here I would like to briefly talk on some ongoing works. I'm trying to determine this inter and intra-annual variability of T and ET ratios for grain only, graze grain and graze out wheat under conventional till and no-till conditions using eddy covariance data collected in our green farm since fall 2016. So here are some results that that's showing the seasonality or the seasonal dynamics of ET, T, and E for these differently managed conventional and no-till wheat fields. And then also planning to continue similar works in native prairie grassland for the entire year, how they work for those, how that ET partitioning works or look like in 12 months, the entire year. And compare FVS partitioning and other partitioning methods. Perform sensitivity analysis for water use efficiency algorithms and try to validate partition output using independent measurements. Collect eddy covariance data from fallow and crop fields for the same season to assist or validate ET partitioning work. So we started doing this from this summer. We have a cover crop, grains, forest sorghum, forest soybean, and fallow fields. And we are monitoring soil moisture dynamics and ET, all that this summer. Thank you. I will address if you have any questions.